Let's go ahead and look at these first two warm-up problems. So just to read it so everyone can see it, hear it. There's the first one says, find an integral representing the area bounded by f of x equal to the square root of x, g of x equal to 6 minus x, and the y-axis. So I'll point out, sometimes they'll, instead of saying the y-axis, they'll tell you that the other boundary is x equal to 0. Just be careful. It's easy to accidentally mix those up and think that x equal to 0 is the x-axis, but x equal to 0 is the y-axis. So for this first one, we're looking at this region here. And certainly if I had any choice about it, I'm going to do this one using vertical cross sections or vertical strips because they're going to be nicer. So my strips are going to be like this. And the reason I'm picking vertical strips here is because no matter where I draw the strip in my region, the upper boundary and the lower boundary, well, I should say the upper boundary is always 6 minus x, and the lower boundary is always the square root of x. So I'm thinking about the area of a cross section. That's going to be my height times my base, which is going to be the height's the top function minus the bottom function. That's going to be my 6 minus x minus my square root of x times my base, which is a small change in x, dx. Can you all see that okay? If you need me to zoom in, I'm always zoom in. And then if I want to find the total area, well, we're going to, in quotes, add up all of the rectangles, meaning we're going to integrate. We're going to integrate from, well, we'll talk about those limits of integration in a second. We're going to integrate from something to something of 6 minus x minus the square root of x dx. So the question now becomes, what are the limits of integration? How far left can I draw a rectangle? Or how far left does my region go? Well, it looks like 0, and it is 0. That's not the hard one. The harder one is figuring out where these two things intersect. What's going to happen a lot in problems like this is that people have thought about the problem ahead of time and tried to make it not terrible. It's usually going to intersect at a place that's nice. So you could certainly try to find the point of intersection by setting the square root of x equal to 6 minus x and squaring both sides and bringing everything to one side and then solving for x and x getting x equal to either 4 or negative 9. Or you can make some smart guesses. If you make a guess here, well, if I'm taking the square root of x, I don't want to guess something like 3. Square root of 3 is terrible. I want to get something like 1. 1's not right. The square root of 1 is 1, and 6 minus 1 is 5. Those aren't. Let me guess the next nice number, which is 4. And the square root of 4 is 2, and 6 minus 4 is also 2. So at that point there, we can really relatively easily guess as x being 4 and y being 2. So a lot of the time, it's going to be worth your time just to make a smart guess instead of doing this. And then bringing everything to one side and getting 0 equal to 36 minus 13x plus x squared, and then factoring that as x minus 4 times x minus 9. Right, that's more work. If you can guess a nice answer, yes. So that's our upper limit, which is x equal to 4. And there's the area represented as a single integral of that region. Questions about that one before we do the next one? Okay. So here's the attendance form for those of you on Zoom again. So for the next one, it's the same functions, except now we're bounded by f of x equal to the square root of x, g of x equal to 6 minus x, and the x-axis, which is also y equal to 0. So now we're looking at this region down here. And although one could use vertical cross sections, it's going to be disadvantageous to do so. So use vertical cross sections, I'm going to be stuck writing 2 intervals because I'd have to break it up. In fact, we could, right? So I will actually do it both ways because why not? So using vertical cross sections, we have to break it up here. From 0 to 4, we're going to get the integral from 0 to 4 of our height, which is the square root of x, times our base, which is dx. And then for this section here, we're going to go from 4 to 6 of our height, which is the function 6 minus x, times our base, which is dx. It's actually not that terrible to do it with two intervals, but I will tell you the default preference for most people is to write it as one interval. Even if writing it as two doesn't seem that bad. So writing it as one integral, we would have to use horizontal cross sections, horizontal strips. If we're going to use horizontal strips, then we have to do, or I should say this is vertical strips, vertical cross sections. I will use strips, rectangles, cross sections kind of interchangeably. So, but over here using horizontal strips or cross sections, well, then we have to do strips, not stripples, strips. We have to do right minus left. So the area of a cross section is going to be the right function minus the left function times our thickness or our width, which is now a dy. And this is where we have to be extra careful. We can't just write 6 minus x minus the square root of x, dy. Your d whatever has to match the variable that we're using. So you have to change both those functions to functions of y. So g of x equal to 6 minus x. If you've got y, I keep grabbing this pen, I'm sorry. If you got y equal to 6 minus x, if we solve for x, we're going to get x equal to 6 minus y. That's going to be our right function. And then our left function, well, our left function was y equals square root of x. If we solve for x, we're going to get y squared equal to x. So our left function is going to be x equal to y squared. So that's the area of our rectangle or our cross section. And then the total area is going to be the integral from as low as y equals 0 to as high as y equals 2 of 6 minus y squared dy. And technically, if someone was trying to be very kind of not kind about this problem, they would only accept this answer because the question they wrote was find an integral. I've seen people do this before. I don't expect this to happen, but I will tell you, I've seen people write questions like that before where the intention was kind of sneaky and they wanted you to write a single integral. So I don't really think that's going to happen, but I just need to be aware. Questions? Go ahead, yeah. Why don't I do the Oh, so what I'm writing there is so I'm writing the area of a cross section. So I'm saying it's just the area of this little rectangle I've drawn, not the entire area. And then the idea is when I go from there to there, what I'm doing is I'm essentially adding up all of the areas of the rectangles. So it's like I'm going from as far down as all the way down there with that rectangle, and then there, and I'm just adding them all up, which is why we're integrating. But really, to answer your question, which is a good question, the reason I'm doing this is because when we start talking about like volumes, we're going to start thinking of slices being discs, and then we're going to add up all the discs. Or when we do cylinders, slices being cylinders, or when we do surface area, we're going to add up all these rubber bands. So the idea of taking a strip or a cross section or a slice is very useful because then you can say, okay, well, if I can find the area or volume of my whatever thing, then the adding them up part in quotations is really just the integrating. So I kind of like to do it step by step that way. I feel like it's on the other hand. No, okay, fine. All right, let's talk about volume. So, volume. We're going to do two volume examples that are not my favorite, but they do occasionally come up. So let's look at this first one. I should say this type of volume question is maybe the least often asked, but it is occasionally asked. So we want to find the volume of the quote unquote tent shaped solid formed by the intersection of 2 quarter cylinders of radius 3. And I will draw it. Of radii 3, sure, radii, radiuses. So here's what I mean by this. I mean, we'll see how good I can draw this here. Maybe, yeah, it's gonna come out all right, I think. Speed it a little bit. So I'm gonna try and know what happens here. So here's one of my cylinders, quarter cylinders of radius 3, and I'm going to intersect that with another cylinder perpendicular to it, also radius 3. So I'm going to say this other cylinder here can come out this way. That's all right. Okay, got this weird. So that kind of shape in the middle there, that kind of tent shape is what I'm looking at. So just looking at that, let's like pop that out here. Here's my tent shape. I'm gonna make it a little bit bigger. So there's the tent shape in the middle I'm talking about. And the radius of this quarter cylinder is 3, so that should have a length of 3, that should have a length of 3, that should have a height of 3. So how am I going to do this? Well, the idea for this kind of problem and the next problem is to kind of add up a bunch of cross-sectional areas. So let's say that we're going to go to, how do I want to say that? I want to say it the right way? Yeah. Let's say, I'm trying to think about this. Yeah. Let's say I want to go up here to a height of x. And we're going to say that the square I'm about to draw I don't know what the side length is, but let's say that that's a y and that's a y. This has some thickness here. So the volume of my slice, this horizontal slice through the thing at a height of x, the volume, at least from the very beginning, is not too terrible. It's just going to be the area of that square, y squared, times the thickness of that square. And since I'm thinking of the up-down direction as my x direction here, the thickness of my square is a small change in x. So it's a dx. So there's the volume of just that one slice. And now the goal here is to add up all the slices. But before we can do that, we need to figure out what the area actually is in terms of the variable we're going to use. So let's give ourselves a little bit of a favor here. I'm going to draw just part of this here. I just look at kind of the back face here for a second. There's my back face, and we're saying, okay, we're at a height of x, and we're saying that this length in red here is y. And I would really love to get y in terms of x. So what I'm going to do is I'm going to draw a radius, because we know that the distance from the center to the edge of the circle has to be the radius, which is 3. So it looks like I could probably write y in terms of x, because we have a right triangle here, and x squared plus y squared is equal to 3 squared. So it looks like y squared is equal to 9 minus x squared. And I don't even really need to solve for y here, because I'm trying to figure out what y squared is. So I can just pop that in for y squared and say, okay, the volume of my slice here is going to be 9 minus x squared times dx. Or you could have solved for y and said y is the square root of 9 minus x squared, and then plug it. All right, now we're going to add up all the slices. How low do my slices go? What's the low? So if I'm thinking that we're at a height of x here, the lowest height would be 0, and the highest height would be 3. Right, if I'm thinking about, that being x equal to 0, and this being x equal to 3. So the total volume is going to be the integral from 0 to 3 of 9 minus x squared dx. And the idea again here is that we're just adding up a bunch of cross sections, each having the same sort of formula. They're all squares, and we're just adding up the, I mean, I guess they're all technically parallel height beds, right? They're squares with a little bit of thickness. They're all volumes that have a square shape that we're adding up. And so then if we do this, we can actually calculate this, right? This isn't that hard to do. Or I should say it's not that terrible. We get 9x minus x cubed over 3, evaluated from 0 to 3. That's going to be 9 times 3 minus 3 cubed over 3 minus 0 minus 0, which ends up being 27 minus 9, which is 18. 18 units cubed, whatever our units are. If they don't tell you units, you don't usually give units in your answer. So yeah, the volume's 18 whatevers. So we're going to look at another example kind of like this, or in the same sort of vein, and then we will move on to the more typical volumes of revolution, which are washers and discs and cylinders, or shells, essentially, which are the much kind of more typical ones. But sometimes people kind of stress this a lot, so I wanted to make sure we did at least a couple. So questions about this one before we move to the next one? Okay. With another one. Yeah, we'll do it that way. So this next one I will fully admit, I know what I want to ask. Actually writing it out always feels like a challenge. So here's what we're going to say. We're going to say that the region in the XY plane bounded by, now we'll do that, y equal to 16 minus x squared, and the x-axis has cross sections perpendicular to the y-axis that are semicircles. Find the volume of this shape. First of all, let's try and draw the thing. Not that you have to draw the thing to be able to do a problem with it, but it really is going to happen. And really, I say it so emphatically because I'm like, I hope I can draw the thing. It's not impossible to draw, it's just not super easy. So when you have one like this, where you've got a region in the XY plane, and then you're essentially taking cross sections perpendicular to one axis and getting things that are popping out of the XY plane into the third dimension. So I'm going to draw the shape in the XY plane first, which is not too terrible. It's just your downward opening parabola, y equal to 16 minus x squared. And then I only want the region bounded by that and the x-axis. So I'm really just looking at this region. I suppose I could find the points of intersection. That's going to be 4, 0. That's going to be negative 4, 0. And that vertex is going to be 0, 16. And now here's the idea, which we're going to try and translate to 3 dimensions. But the idea basically is that if you take a cross section perpendicular to the y-axis, what should be popping out of the 2-dimensional region is a semicircle. It doesn't look that great from this vantage point. So let's redraw it so that we have things looking like this. Let's see. Yeah, I think we'll do it like that. So I'm going to draw, I'm going to rotate things. So I'm going to think of my XY plane as kind of lying flat on the ground. My x-axis is here, my y-axis is here. Here's my parabola, which looks like this. I'm drawing it dashed on the other side because I know I'm going to kind of pop up out of it. And then here's the cross section that I was trying to draw before. Perpendicular to the y-axis, and then there's my semicircle. perpendicular to the y-axis, there's my semicircle. Hopefully that's a little bit more easy to see what I mean by this kind of shape here. So I don't know how to describe that with words. It kind of looks like a funky loaf of bread. Maybe it's like a whole loaf of bread and you cut it down the middle. So you've got like just kind of half of it. Kind of. That's not the best description ever, but I've heard worse. So picture notwithstanding, we can still figure out what's going on. So what we need to do is we need to figure out how to think about a cross-sectional volume. So I want to figure out what's the volume of this little slice right here. Let's draw that better. There's my slice. Wow, a better, ooh. Okay. Okay, that turned out. That's the slice I'm talking about. With a width of a change in y. And if I want to find the volume of this shape, I need to find the area of that semicircle and multiply it by dy. So the volume here is going to be whatever my area is times the thickness dy. And that's the volume of my cross section or of my slices. I'm probably going to start saying things. Okay, the area of a semicircle is 1/2 pi r squared. So the volume of my slice is going to be 1/2 pi times my radius squared times my dy. So we have to figure out what that radius is in terms of y. Okay, let's go back over to the function here. So we know that our parabola is y equal to 16 minus x squared. And I would love to find that distance there because that distance is my radius. It's how far I am over from the y-axis. Okay, well, if we're at a height of y, then we know that the radius, which is the x value, we can find. So essentially the radius here, if this is the point x comma y, the radius is the x coordinate. So if we solve this for x squared equals 16 minus y, x equals plus or minus the square root of 16 minus y. And if I just want the right-hand side, because I want to find the distance from x equals 0 to the right-hand side, it's going to be x equal to the positive square root of 16 minus y. So that's our radius. It's the square root of 16 minus y. Let's think about that for a second. If we're at the bottom here, where y is 0, the radius should be the square root of 16 minus 0, which is 4. If we're up here at the very top, where y is 16, the radius should be the square root of 16 minus 16, which is 0. That seems reasonable-ish. And then somewhere in the middle, like right here, if y was equal to, I don't know, let's say 7, then the radius is going to be the square root of 16 minus 7, which is 3. Okay, that seems not unreasonable. All right, the rest of this is not too awful. Our total volume is going to be, we're going to add up all the slices, and it's going to be 1/2 times pi times my radius squared times dy, from as low as y equals 0 to as high as y equals 16. If I were solving this, I would do two things immediately. I would bring out any constants. So I would write this as 1/2 times pi times the integral from 0 to 16. And we lucked out here. The square root of 16 minus y squared is just 16 minus y. And the rest of this is not too terrible. It's going to be 1/2 pi times 16y minus y squared over 2, evaluated from 0 to 16, which will be, I don't know, something, 64 pi, I think. You should check on your own. So I'll reiterate, these two examples are kind of atypical as far as volume is concerned. We don't usually spend a whole lot of time talking about these ones, but sometimes people do talk about how you can have a region in 2 dimensions and have cross sections that are semicircles, or circles, or squares, or equilateral triangles, or other terrible shapes. So this problem, if I change this problem just a little bit and said that instead of having the cross section be a semicircle, if I said it was a square whose base was that cross-sectional length, then my area, instead of being 1/2 pi r squared, would have been just whatever that length was, which is 2 times r, which is 2 times the square root of 16 minus x squared, squared. If I had said they were squares instead of semicircles. People occasionally like to ask questions like this. I don't particularly, you might have heard from my tone, I don't particularly like this kind of question. I don't think they're that great. I think the other types of volume questions are more interesting and more fun to do, but someone could ask a question. Move on to the more fun stuff. So yeah, let's talk about this example first. So we want to set up the integral for the volume of the region bounded by y equal to 3x minus x squared and the x-axis around the x-axis. It is almost always going to be in your interest to draw the region. Your drawing does not have to be perfect. It just needs to be reasonably representative of what's happening. So y equals 3x minus x squared. The way I'm going to think about graphing that is by finding the x-intercepts. So I'll point out that this is going to be y equal to x times 3 minus x. Cool. The x-intercepts are 0 and 3. So 0, 1, 2, 3. And it's a downward opening parabola because it's a negative x squared. So it's going to look something like that. And I'm not going to draw the rest of it because I really only care about the region that's between the x-axis and my function y equals 3x minus x squared. So we're looking at this region and we're rotating around the x-axis. And if you, well, I don't want to say that. So in this class, you can kind of use any method you want typically. If you are specifically trying to use the disk method or the washer method, which are the ones we start off with, your vertical strip, sorry, let me scratch that. Your strip, vertical or horizontal, should always be perpendicular to the axis of rotation. And I'll just give you a preview of what's happening here. Later on, we'll talk about the shell method. The shell method is easy to remember because shell means parallel. So if you're doing shell method, your strip should be parallel because shell rhymes with parallel. If you're doing the disk method or the washer method, which are the same, you should use a perpendicular strip, perpendicular cross section. And we'll see why in a second, but that's something that I want you to all remember. Shell means parallel, and then the other method, the disk/washer method, means perpendicular, always. So based on what your region looks like and what kind of strip you decide you want to use, that will fully determine what method you're going to have to use to find the volume of your shape. And here we're going to use a vertical strip because of a couple of reasons. One, using a horizontal strip would be hard, right? If I use a horizontal strip, I need to write my x as a function of y, and I don't want to solve x as a function of y here. It's doable, but it's more work than we need to do. So if things are already written as y as a function of x, if you don't have a good reason to change things around, you should just leave it that way and use a vertical strip. So if y is a function of x, your strip should be vertical. All right, so now we're going to rotate this thing around. And again, I do think you should draw this picture. I don't think you need to draw the next picture I'm going to draw, which is essentially we're just rotating the shape around the x-axis. So draw this here like that. Really, I'm just drawing the same shape and I'm doubling it over or reflecting it over. Well, kind of. And then you're thinking about having some sort of volume there. So you rotated this thing around. But really, what I really want to think about is the fact that I'm taking this strip and rotating it around and getting what I like to call a disc, or often call a slice. So that slice I want to find the volume of, I should really say disc because it is a disc. The volume of my disc, well, it's the thickness, small change in x, times the area. It's the area times the thickness. But the area, well, that shape is a circle. So the area is going to be pi times whatever the radius squared is, times dx. But the radius is literally just whatever the function height is. So here our radius is just going to be the function 3x minus x squared. And then we're squaring that. So here, the volume of this shape, total volume, is going to be represented by the integral from x equals 0 to x equals 3 of pi times your radius squared. I don't know. I have too many brackets there, but oh well. You don't really need the second brackets. And that's how we would express this as a volume. I should say, that's how we'd express this volume as an integral. We then could actually calculate it. So I'll tell you, people are going to start focusing less on the calculation part and more on just like, yeah, we can set it up, and doing the rest of this should be thought of as straightforward. Now, let's still do it just to practice it. I would immediately bring out the pi, integral from 0 to 3. We're going to FOIL this out, and 3x minus x squared times 3x minus x squared is going to be 9x squared minus 6x cubed plus x to the 4th. And then we're going to antidifferentiate. We're going to get pi times 9x cubed over 3 minus 6x to the 4th over 4 plus x to the 5th over 5. From 0 to 3, 9 over 3 is 3. 6 over 4 is 3 halves. So we're going to get pi times 3 cubed minus 3 halves times 3 to the 4th plus 3 to the 5th over 5. And I wouldn't write anymore. I would think about the fact that when I plugged in 0, I'm going to get minus 0 plus 0, which is still 0. So I'm just going to leave it like that. And no, I don't think you should go any further here. I don't think you should try to simplify this unless you really have a desperate need to. Okay. Let's look at another example. One thing, I'll say that in a minute. Okay, volumes all day. Times it. Yeah, we got plenty of time to talk all about the volumes. So let's do the following. We want to find the volume of the solid formed by revolving the region bounded by y equal to the square root of x and y equal to 1/9 x about the x-axis for the first part. But you might see that we're going to do another one too. So we're going to look at the y-axis as well. All right, well, let's draw it. These are two not terrible graphs to draw. Y equal to the square root of x is your usual square root shape. And y equal to 1/9 x is some straight line through the origin that's a pretty shallow slope. It's going to look something like this. And we could certainly find where they intersect. I actually don't know where they intersect. I take a guess, but I might have to guess too much. So here it might actually be worthwhile to just let them equal to each other. If we set square root of x equal to 1/9 x, I would probably multiply both sides by 9 first and say 9 root x equals x, and then square both sides and get 81x equal to x squared, and then 81x minus x squared equals 0. X times 81 minus x equals 0. So either x is 0 or x is 81. So this point here is the point 81 comma square root of 81, or 1/9 times 81. Either way, 9. Okay. So we're trying to find the volume of this region revolved around the x-axis. I'm still going to do the same thing I did before, which is draw a representative strip that is perpendicular to my axis of rotation. Because we're still in the land where we're only talking about the disk/washer method. And the reason I keep saying the disk/washer method is because they're really the same idea. The washer method just has an additional little piece to think about. So here's my representative strip or cross section. And when I rotate this around, yeah, I'm going to draw the whole thing. When I rotate this around, if you want to try and draw the rotation, by the way, what I would say is just draw the same shape and reflect it across the axis you're rotating. So when I'm going to draw this, I'm going to draw the outer part as solid and then reflect it this way. And then the inner part is kind of dashed. So what we have here is kind of this weird bowl shape with like a cone cut out of it. So it was, if you hadn't done this lesser part, you'd have like this kind of solid paraboloid thing, and then you're essentially digging out a cone's worth of volume from it. So you have some sort of weird bowl where the inside's a cone instead of just a regular bowl shape. So in the middle here, for my little cross section, what's happening is we have a slice like this, except we're completely missing the inner part right here. So we have a washer. And our washer, I ran out of room over here. Sorry, I'll put it down here. So this washer, which is centered on my x-axis, right? The volume of my washer is going to be, well, it's going to be the area, which is the big circle minus the little circle, times the thickness, which is still a small change in x. So it's going to be your big circle, which has an area of pi times your big radius squared, which we'll write down. Oh, you can't quite see that, sorry. Minus your area of a little circle, which is pi times your little radius squared, all times your thickness. Let me go back and label things here. Your thickness is just the width. Your large radius is right there, and your smaller radius is right there. Your larger radius is the function that's further from the axis of rotation. So here, the larger radius is the square root of x. Your smaller radius is the function that's closer to the axis of rotation. So your smaller radius here is going to be 1/9 x. So then setting up just the volume of the washer, it's going to be, people usually factor out the pi because they can. It's going to be pi times the larger radius square root of x squared minus the smaller radius 1/9 x squared dx. And then we do the usual thing where that's the representative slice volume, and then we're going to add up all the slices by integrating. So the total volume is going to be the integral from 0 to 81 of pi on the outside times the square root of x squared minus x over 9 squared dx. Yes, I wrote x over 9 instead of 1/9 x, the same thing. And then if you wanted to, the simplification we could do here, we're not actually going to finish this one. We're just going to write it as the integral from 0 to 81 of x minus 1/9 x squared. Sorry, 1/81th. Apologies. 81th, 81st, I don't know. 1 over 81 times x squared. So that then you could easily anti-differentiate that. You get x squared over 2 minus 1 over 81 times x cubed over 3, plug in your limits of integration and find some terrible number. So the difference between the washer method here and the disk method before is that in the previous problem, there's two ways I like to say this. In this problem, you can either say the region we were rotating was flush with the axis of rotation. Speaking of which, I don't know if it was there's some class has a Weber problem where they talk about how the region abuts the axis of, that's abuts just means next to. A-B-U-T-S, I think is how you spell that, abuts. Anyway, if your region is flush with the axis of rotation, or it's like you could also say if the axis of rotation is one of your boundaries. Oh, this one was bounded by y equals 3x minus x squared and the x-axis, and we're rotating around the x-axis. Clearly, the x-axis is one of my boundaries, so we're going to use the disk method because there isn't any missing region between your region and your axis of rotation. Whereas in the second problem, we clearly have some separation between the region and the axis of rotation. The region is not flush with the axis of rotation, or the axis of rotation is not one of the boundaries of our region. So that's almost always going to call for this washer method where you have to subtract out the smaller circle area or volume if you're multiplying by dx. Cool. Questions before we go the other way? All right, let's go around the y-axis. Again, I guess I'll draw it again. So same region, rotated around, this is part B, I guess, rotated around the y-axis. Draw it again. Okay, so for now we're stuck using the disk method or the washer method. Meaning, if you're stuck using one of those two methods, the same method really, you always have to pick a strip that is perpendicular to the axis of rotation. Since we're going around the y-axis now, we have to pick a horizontal cross section or a horizontal strip. And when I draw this, I really don't actually like to draw the whole thing rotated around because I'm not good at drawing. But what I do like to draw is my strip rotated around the axis. I'm gonna just drop it down to below here, and then I'm gonna draw my rotation. It's gonna look like that. You don't have to draw this. It just feels nice to draw it. So we can see that, oh yeah, we really do have a washer. And the volume of this washer is going to be, well, you've got a larger radius. You've got a, sorry, I didn't leave myself enough room here, a smaller radius. And the volume, once again, is going to be pi times your large radius squared minus pi times your small radius squared times the thickness of our slice, which is a small change in what? Small change in X or a small change in Y? Small change in Y, right? Because you've gone up, down, not left, right. So this little thickness here is a small change in Y. That's telling me, and really we should get used to the idea that if you're using a horizontal cross-section, dy, using a vertical cross-section, dx, every time. That's telling me that all my things have to be written as functions of y, not functions of x. So my outer radius here, which I can see from my picture, is going to be coming from the function y equal to 1/9 x. I need to rewrite that as 9y equal to x. So that x is a function of y is x equal to 9y. Or if you like, you can even write it as like f of y equal to 9y. But really, we just need this. That's my outer radius. So my outer radius here is going to be 9y. My inner radius, well, that's coming from the other function. We're coming from this function, which is y equal to the square root of x. So we're going to solve for x, and we're going to get y squared equal to x. So my inner radius is x equal to y squared. So I guess I just want to write y squared here. Fine. Plus, what I'll say about that is, if you didn't draw the picture, it'd be really hard to figure out which one was the inner one, which was the outer. But you could figure it out by saying, well, I know these are intersecting at 0, 0, and 81, 9. So pick a value between 0 and 9, like say 1. 9 times 1 is 9. 1 squared is 1. The 9 is the bigger value, so it's the one that's further away from the axis of rotation. But again, I really have to say you should draw these. You should always try and draw these regions to rotating. At least you just have an idea of what the region looks like. You don't have to draw the rotation, but you really do want to draw like that region there so you can see what's happening. So then that's going to be pi times, I'm factoring out the pi, we do 9y squared minus y squared squared dy. And then my total volume, I'm just going to add up all the slices or all the washers. It's going to be the integral from as low as 0 to as high as 9 of pi times 9y quantity squared minus y squared quantity squared dy. I know we can simplify this, but often if you're just asked to set these up, it's probably better if you don't actually square this out. So that the person reading your work can be like, oh yeah, they know that they're just doing the radius squared. But if you do simplify it, it's going to look like pi times the integral from 0 to 9 of 81y squared minus y to the 4th dy. Which again is not something that is terrible to, I mean, the numbers are not nice, but it's a relatively straightforward integral. Power rule, plug in your limits of integration, done. Okay, let's see what we got here. All right. Let's look at a different region. Yeah, let's look at a different region. Let's look back at the region we started class with. Specifically, this region up here, the one that's next to the y-axis. We'll write it again, but that's what we're going to look at for a second. So yeah, again. So our region, once again, is bounded by y equal to 6 minus x, y equal to the square root of x, and the y-axis, which is the line x equal to 0. Draw it. So we're looking at this lovely region over here. So we're going to start by revolving it around the x-axis. So I'm going to revolve around the x-axis. We're going to use a vertical strip. I'll remind you all that this point of intersection is the point 4, 2. And I want you all to set up the volume of your washer. So the volume of your slice, or the volume of your washer, should be big circle area minus little circle area times the thickness. I'll start drawing it, but I want you to try and write it. You're on your own. So you can't read what I've written because it's kind of terrible looking. That's big circle minus little circle all times the thickness. I think I forgot an S there. Right. See, it's the big circle. The radius is 6 minus x. The little circle, the radius is square root of x. So the volume of my washer here is going to end up being pi times the big radius squared minus the little radius. I'm going to change my language there just a second. The big radius is the function that's further from the axis of rotation, and the little radius is the function that's closer to the axis of rotation. So 6 minus x squared for the further from the function from the axis of rotation, and square root of x closer times dx. And then the total volume would be the integral from as far left as 0 to as far right as 4 of pi, put out in front, times the same thing. 6 minus x squared minus the square root of x squared dx. Yeah, I need another page for this next one. What if instead, I really would love, I want to not draw it again, but I kind of have to draw it again. So what if instead we wanted to revolve, it's like here. Now we're going to revolve around the line y equal to -2. I wish I could just have a copy of this picture already drawn here. So same region. Same enough. But now we're revolving around, instead of the x-axis, revolving along the line y equal to -2. So our region is now 2 whole units further away from the axis of rotation. Or in other words, each of our radii are just going to increase by 2. Let me show you what's going to happen. So if I do the same sort of thing, I draw my strip perpendicular to my axis of rotation, and then bring it out here. And watch my picture. I'm rotating around now this line down here. So my smaller radius is that length right there. So I'm going like all the way down there. And my larger radius is even bigger. It's going to be that much, that much. So there's my new washer, which is much wider. Has a bit much larger diameter. And the volume of this washer, still the same idea. It's going to be pi times the large radius squared minus par times the smaller radius squared times your thickness. Now the large radius isn't just your bigger function, it's your bigger function, I should say, it's the difference between your bigger function and the axis y equals -2. So my big radius here is going to be difference between y equals 6 minus x and y equals -2. I don't really want the y equals parts there, but I want to point out that we're subtracting the same kind of thing. We're subtracting something that y is equal to minus something that y is equal to. So we're going to end up getting 6 minus x minus -2, which is going to end up being 8 minus x. Or in other words, my radius got too bigger. Right? Before it was 6 minus x. Now it's 6 minus x plus 2. And similarly, the smaller radius is also going to get larger in the same sort of way. It was square root of x. Now it's going to be the square root of x minus -2, which is the square root of x plus 2. We could have been doing this the whole time. We could have said, oh, the radius here really is the difference between your function 6 minus x and its axis y equal to 0. And the difference between 6 minus x minus 0 is just 6 minus x. We just don't talk about it that way because we don't need to. But it's always the difference between your function and whatever the axis of rotation happens to be. So here, if we set this up, we're going to end up getting the volume of your washer equal to, I'm actually not going to write it in a simplified way. I'm going to write it as pi times your 6 minus x minus -2. That's kind of annoying, James. Squared minus your pi times your square root of x minus -2 squared. And then the total volume still has the same limits of integration. We're still going from 0 to 4. And that's going to be pi times all that. Which is definitely worse. Because if you actually have to solve this, you have to square these things out. So 8 minus x quantity squared is not wonderful. It's going to be x squared minus 16x plus 64. And this thing squared is going to be x plus 2 root x plus 4. And then you have to add those all together and then anti-differentiate all like 5 or 6 of those terms. So when you have a different axis of rotation, things get ugly fast. Let's look at one more axis of rotation here, and then we'll talk about the shell method a little bit. So there's one more axis I want to revolve this around, which might feel kind of weird. But now we're going to revolve the same region around the line y equal to 8. Same region. Did I leave myself enough room? Maybe. Sure. Region, and I'll remind you that intercept was 0, 6. This intercept was 6, 0. And here's the line y equals 8. Probably could have left myself a little bit more vertical space there. Oh well, I did not. Same idea once again. We're still going to draw a strip perpendicular to our axis of rotation, and then we're going to revolve that around the axis of rotation. So drawing this way over here. No, I should go over there. So here's my strip again. I'm going to try and revolve that around this line here. So it's going to look like this. Great. That's pretty good. So then, and here's y equals 8. Here's my inner radius or my smaller radius. And here's my outer or larger radius. And what I want you to observe here is that the outer radius is going to be the difference between my axis of rotation and the function that's further away. And because my axis of rotation is kind of changed where it is in relation to the region, the function that's further away has also changed. The further away function here is the square root of x, whereas in the previous version, it was 6 minus x. So that's why drawing the picture is really, really helpful, because you can see which function is going to get to play the role of the larger radius. So here, if I was trying to find the volume of my washer for the umpteenth time, it's still going to be pi times my big radius squared minus my little radius squared times dx. But now my large radius is the difference between my axis of rotation and my function. So it's going to be 8 minus the square root of x. And I do mean to subtract in that order, because I want to end up with a positive radius. And 8's bigger than the square root of x is on this interval. Technically, when you're using the disk or the washer method, you can make the wrong subtraction and be fine because you're going to square it. So it doesn't matter if it ends up being negative accidentally because you end up squaring it, that's fine. But when you use the shell method, it does matter because you don't end up squaring it. And so you have to be extra careful. So we should just be careful all the time and make sure that we're subtracting in the right way so that this value ends up being thought of as positive. So our large radius here is 8 minus root x, and our smaller radius is going to be 8 minus 6 minus x. So here the volume of our washer is going to be pi times the large radius squared, so 8 minus root x squared minus the small radius squared, which is 8 minus 6 minus x squared dx. And then finally, we would solve the same limits of integration because that strip still only gets to travel as far left as 0, as far right as 4. So our total volume is still going to be an integral from 0 to 4, holding the pi out in front. And then we've got 8 minus root x squared minus, you could simplify this, right? 8 minus 6 minus x is just 2 plus x, but I'm going to write it this way. But if you were doing the integral, you would definitely simplify that before you squared it out. So different axes of rotation means your radius is not just your function, but the difference between your function and whatever the axis of rotation actually is. Kind of a lot. There's more, but wait, there's more. So disk/washer method, really the same method. The washer method just has the added fun of subtracting out the inner smaller circle with the smaller radius. The shell method, on the other hand, is a different animal. Let's look at, do I have an example teed up? I mean, no, but I can make one up real easily. So, yeah, I know what we'll do. So let's go back to the original, the first thing we rotated, but now rotated across the y-axis instead. So let's say we want to take the same region, the region bounded by y equal to 3x minus x squared, and the x-axis, also known as the line y equals 0. But now we're going to rotate it around the y-axis. So we're going to get something like, try to be good with our numbers here, 1, 2, 3. Sure, and 4 is too big. Try to make this look somewhat nice, about like that. So there's our region. And the problem here is that while it is technically possible to solve for x as a function of y, it's not particularly easy. Like, it's not that terrible. You can complete the square here and do some stuff, but it's not fun. And we don't need to do that to be able to do this integral. So To do this, we're going to use still a vertical strip. But now you might notice that our strip is parallel to our axis of rotation. And when the strip is parallel, we have to use, thank you, the thing that rhymes with parallel. Parallel shell. Parallel shell, parallel shell, parallel shell. Say it enough times. Saying the L's is kind of hard. Parallel shell. Okay. So specifically, when we rotate this strip around the axis of rotation, look what happens. We get what is often referred to as a cylindrical. Whoa, can I draw? Ugh. A cylindrical shell. Sorry, my drawing here feels like it's not the best. But you've got this shell of a cylinder, or as I like to think of it, like a pipe. Like a pipe is a shell of a cylinder. It's got some thickness to it, but the center is hollow. So here's your shell of a pipe. And we want to find the volume of that shell. So to find the volume of this shell, we're going to think about cutting it right here. Not right there. And unraveling it. If we do that, it's going to look like there's the place where I cut it. And then it's going to look essentially like a long rectangular slab. There's the end of the cut that it meets up with. And the volume of that slab, well, it's got some thickness, which is dx, right? Because it's just coming from that there. And it's got some height, and the height is just whatever the function is. And the length is not the radius of the circle, but the circumference of the circle. So that's going to be the circumference, which is going to be 2 pi times the radius. So what's the radius? So this always used to trip me up. The radius is just how far from the axis of rotation we are. So we're going to say that, well, we're a distance of x from the y-axis. If we're going around the y-axis, the distance is x. So our radius here is just x. And our height here is just 3x minus x squared. So for this particular shape, the volume of our shell, I usually write it as 2 pi times r times h times d, whatever is appropriate, or length times height times thickness, and then substitute in the appropriate things. The radius is x, the height is the function, and dx is dx. So there's the volume of our shell, and then we're adding a bunch of shells together. So, right, another shell that was further in would have a higher height, and then I would try to draw the shells, but not very good. There are good pictures in your book of like shells kind of in each other that are kind of like nesting Russian dolls, kind of ish, where you've got like a big wide shell, and then a less wide but taller shell, and then less wide, taller, kind of like that. So you're kind of taking them out from one another. I'm not describing it the best, but you kind of get the idea. I wish I should have brought a picture with me, but it didn't. So to find the volume of this, we're going to get the integral from, well, x goes from as far left as 0 to as far right as 3. So it's the integral from 0 to 3 of 2 pi times your radius x times your function 3x minus x squared dx. And normally we would immediately pull the 2 pi out in front and then distribute the x and get 3x squared minus x to the third. And then we would anti-differentiate. We get 2 pi times the integral of 3x squared is x cubed. The integral of x cubed is x to the 4th over 4. We go from 0 to 3. And we end up getting 2 pi times 3 cubed minus 3 to the 4th over 4. Minus 0, minus 0. So whatever that ends up being. It's going to be 2 pi times 27 times 4 is 104. 100, right? Yeah. No, 108. And 108 minus 81 is 27. So 2 pi times 27 over 4, which is going to be 27 pi over 2. There's your volume. So when you're doing integrals of when you're finding volumes of rotation via integration, often you will have a choice about which way you want to do it. Let me show you an example. Let's say that we were rotating the region bounded by y equal to x cubed and y equal to, what I like here, 4x in the first quadrant about the y-axis. Find the volume. So let's draw it. So y equals x cubed looks vaguely like this. It's not the function I'm best at drawing. And y equals 4x looks something like this, and they do eventually intersect. Yes, they would intersect down here as well, which is why I had to specify that we're only looking at the first quadrant. Otherwise, we'd have to look at both quadrants. We can find the points of intersection by setting x cubed equal to 4x, or x cubed minus 4x equal to 0, or x times x squared minus 4 equal to 0, so that you get x equal to 0 and x equal to plus or minus 2. We don't really care about the minus part. So that point's 0, 0, and that point's 2, 8. And now you have a choice. If we're going around the y-axis, you could either choose to use a vertical strip, which is parallel, which means we'll have to use shell, or you could choose to use a horizontal strip, which is perpendicular, which means you have to use the washer method. And if no one specifies which way to do it, you can really do whatever you prefer. If it were me in this situation, I would choose the path of least resistance, which to me feels like not changing my functions to be functions of x. I've already got, functions of y, I've already got y as a function of x and y as a function of x. I would like to keep things that way, which means I'm going to use a d what? A dy or a dx? A dx, which means I'm going to use what kind of strip? A vertical or a horizontal? Vertical. So that's the way I would choose to do it without any other information. I would say I'm going to use a vertical strip because it's the least amount of work, which means I have to use the shell method because I've done it that way. So my volume, doing it with the shell method, well, the volume of my shell, it's going to be 2 pi times the radius times the height times the dx. You should, if you're thinking shell, you should always be imagining that this vertical strip is a horizontal distance of x, or if it's a horizontal strip, you're a vertical distance of y away from the axis of rotation, as long as it's the regular x or y axis. If it's a different axis, we'll talk about that next time. So here, my radius is just x. My height is the top minus the bottom. So my height is going to be the 4x minus the x cubed. So the volume of my shell is going to be 2 pi times x times 4x minus x cubed times dx. Then my total volume is going to be the integral from as far left as 0 to as far right as 2 of 2 pi x times 4x minus x cubed. Or maybe you hate the shell method and you never want to use it unless you absolutely have to. And some people really feel that way. Some people just feel much more comfortable with the disk slash wash method. That's fine. If that's how you feel, then you can use the washer method by using a horizontal strip. And then we do have to change things. So I do like drawing this picture for whatever reason. So we have our inner radius, which is the y equals 4x function. We have to solve for x as a function of y. So our inner radius being y equal to 4x is going to result in getting y over 4 equal to x. And our outer radius would have been, comes from y equals x cubed. We have to solve for x and get x equal to y to the 1/3. So doing it using the washer method, I'm just going to go straight to the integral here. It's going to be pi times the integral of my larger radius squared, so y to the 1/3 squared, minus my smaller radius squared, which is 1/4 y squared dy. And my limits of integration are as low as 0 to as high as what? Maybe sorry if that doesn't look clear what I've written there. It's not a 3, it's an 8. So we're going as low as 0 to as high as y equals 8. And assuming that we've done everything correctly, either way you calculate this, you should get the same volume. So you have to decide what you think is better if you're given the option. Sometimes they'll just tell you, use the shell method, use the disc or washer method, and you don't have a choice. But if you are just given a region and told to rotate it around an axis, you can choose. If you choose a parallel strip, you're using shell. If you choose a horizontal or a perpendicular strip, you're using disc or washer. I shouldn't say horizontal there, right? Because your horizontal strip, right? If we could change this up and say rotate it around the x-axis, and then your horizontal strip becomes the shell method version, and your vertical strip becomes the washer method version. So it all depends on how your strip is oriented compared to your axis of rotation.